SwayamPrabha. Digital India. Educated India.
Welcome to lecture 24 of the course on multivariate data mining methods and applications. The title of this lecture is Backpropagation of Errors Algorithm. In the last lecture, we have discussed the multi-layer perceptron. While using multi-layer perceptron for a given data set, one requires training the model. For training the model, backpropagation algorithm plays a very crucial role. We use the backpropagation of errors algorithm for training multi-layer perceptron or artificial neural network. So, in this lecture, we are going to discuss the backpropagation algorithm and how we can use it for training artificial neural network. We will also discuss the three learning modes, which are online learning mode, stochastic learning mode and batch learning mode for backpropagation algorithm. Now, we consider backpropagation of errors algorithm when we have a single hidden layer. So, suppose this M denotes the set of R input nodes and small m belonging to capital M indexes all input nodes, and this J is the set of T hidden nodes. Small j belonging to capital J denotes the index for hidden node. Then this k is the set of S output nodes and small k belonging to capital K indexes an output node. Then the error signal at kth output node is say E I k equal to y I k minus y curl I k for all k belonging to capital K. Y curl I k is the predicted value of y I k. Then error function or error sum of square is say E I equal to 1 upon 2 summation small k belonging to capital K E I k square. This is the error sum of square for a particular I. And then this is equal to sum over k y I k minus y curl I k square. Error sum of squares for the entire data set is, now we take summation of E I for all I equal to 1 to n. Actually, we have n copies of x's or y's, and then we take 1 upon n here, that is we are taking average of EI's over all samples. So, this is the error sum of square for the entire data set. And then we substitute the value of EI, which is equal to 1 upon 2 EI k square, and then we take summation over k. So, ultimately we get ESS equal to 1 upon 2 n summation over I summation over k EI k square. Then each derivative of ESS with respect to weights is a sum over I of derivatives of EI for I equal to 1 to n. So, minimizing ESS with respect to the connection weights. Your connection weights are alpha I k j and beta I j m. And the minimization of ESS with respect to these connection weights is equivalent to minimizing each EI separately. For the ith input vector, Vik is equal to alpha naught k plus Zi transpose alpha k, where k varies from 1 to capital K. So, when we move from the hidden node and go towards the output node, we get Vik equal to alpha naught k plus Zi transpose alpha k, where alpha k is equal to alpha k1, alpha k2, so on alpha kt transpose. So, obviously, this is T cross 1 and Yik curl is equal to Gk Vik. Gk is the activation function at the output node, and this is for all k. Further, we write alpha I equal to alpha I1 transpose, alpha I2 transpose, so on alpha Is transpose whole transpose, or alpha I k j, this vector. So, ultimately alpha I is T s cross 1 vector, and as I mentioned earlier, alpha I is the weights from hidden layer to output layer. Then we consider the update rule for weights alpha I k j from the jth hidden layer to the kth output node. So, alpha I plus 1 is equal to alpha I plus del alpha I, where del alpha I is equal to minus eta del over del alpha I E I, the first derivative of E I with respect to alpha I. Eta is the learning rate, and then you can write it as, say, the matrix with elements minus eta del E I upon del alpha I j h, or we write it equal to del alpha I k j, this vector. Similarly, we can update alpha I k naught, the weight corresponding to the bias term. Then your problem is to obtain this del over del alpha I j h E I. Remember, E I is equal to 1 upon 2 summation over k E I k square, which is equal to 1 upon 2 summation y I k minus y I k curl whole square. Further, y I k curl is equal to g k v I k, and v I k is equal to alpha naught k plus z I transpose alpha k. Then, to obtain the derivative del E I upon del alpha I k j, we use the chain rule. So, using the chain rule, you can write it as del E I upon del E I k, small e I k, then del small e I k upon del y I k curl into del y I k curl upon del v I k, and then del v I k upon del alpha I k j. Now, del E I upon del E I k you can obtain from here. if we differentiate ei with respect to eik, then we get 2 times eik, and then you have half here. So, ultimately you get small eik here, this term. Then del eik upon del yik curl, eik is equal to yik minus yik curl, and when we differentiate eik with respect to yik curl, we get minus 1. Then del yik curl upon del vik, we use this relationship. So, you get the first derivative of gk, gk1 vik, gk1 denotes the first derivative of gk, and then we differentiate vik with respect to alpha I kj here, and you obtain zij. Actually, in Z I transpose alpha k, corresponding to alpha I k, you have Zij, Zij into alpha I k, and then when we differentiate with respect to alpha I k, we obtain Zij. So, ultimately we can write it as minus delta I k Zij, where delta I k is equal to minus del over del yik curl ei into del over del vik yik curl, and then this is equal to eik into gk1 vik. Del ik is actually the sensitivity or the local gradient of the ith observation at the kth output node. So, if you are moving from the ith observation towards the kth output node, then this is the sensitivity or local gradient of the ith observation. Then the gradient descent update for alpha I kj is, say, alpha I plus 1 kj is equal to alpha I kj minus eta del ei upon del alpha I kj, and then we write the value of this derivative here. So, you get del alpha kj plus eta delta ik zij. So, this is the update rule for alpha I kj. Then update rule for connection from mth input node to the jth hidden node. So, first what we have done? We have updated or we have formed an update rule for connection from a particular hidden node to a particular output node. Now, we form update rule for connection from a particular input node to a particular hidden node. Again, uij is equal to beta ij naught plus xi transpose beta ij for all j. So, actually uij is the weighted sum of inputs to the jth hidden node, and then the ith input vector is xi equal to xi1, xi2, so on xir transpose. Xi naught is obviously equal to 1, and beta ij is equal to beta ij1, beta ij2, so on beta ijr. So, this is the vector of coefficients or the vector of weights from the input node to the hidden node, and then the corresponding output is Zij is equal to Fj Uij. Fj is the activation function at the hidden node. Further, we are writing beta I equal to beta I1 transpose, beta I2 transpose, so on beta IT transpose, whole transpose. We write it equal to the vector with the element beta IJM. So, this is the ith iteration of R plus 1 T vector of input layer to hidden layer weights. So, at the ith iteration you are getting this weight vector. Total number of elements of this vector is R plus 1 into T. Remember, you have R input variables and then x naught is equal to 1, the term corresponding to the bias. And then update rule is beta I plus 1 is equal to beta I plus del beta I, where del beta I is equal to minus eta del over del beta I ei. And then again this is the vector with elements minus eta del ei upon del beta I j m, and we write it equal to del beta I j m. Again we obtain the values of del ei upon del beta I j m. Just like the other weights, we can also update the bias term also, beta I j naught. So, further we obtained del beta I j m using the chain rule of differentiation, and for that purpose we write del over del beta I j k e I equal to, first we differentiate with respect to z I j. So, del E I upon del Z I j, then we differentiate Z I j with respect to U I j, and then we partially differentiate U I j with respect to beta I k j. Further, we can easily obtain del E I upon del Z I j, which is equal to summation over k E I k del E I k upon del Z I j. Actually, E I is equal to half summation over k E I k square. So, we get this derivative, and then to obtain del over del Z I j E I k, again we write it as del over del V I k E I k del V I k upon z, del Z I j. So, we get summation over k E I k, then we differentiate E I k with respect to V I k. So, we obtain G k 1 V I j. The first derivative of G k V I j with respect to V I j is denoted by G k 1 V I j. Further, using the relation between V I k and Z I j, we can easily verify that when we differentiate V I k with respect to Z I j, we obtain alpha I k j, and then we write it equal to summation over k delta I k alpha I k j. Therefore, the partial derivative of E I with respect to beta I j k is equal to summation over k eik gk1. Now we substitute the value of Vik here, which is alpha I k naught plus Zi transpose alpha I k, and then we obtain Fj1 beta I j naught plus Xi transpose beta I j here. The first derivative of the activation function from input layer to the hidden layer, or the activation function at the hidden layer, and then we obtain Xim here. Then from equation 7, 11 and 12, this is your equation 7, this is 11 and this is 12, we obtain delta Ij equal to Fj1 Uij summation over k delta Ik alpha I kj. So, we get this gradient descent update for beta Ijm. Beta I plus 1 Jm equal to beta Ijm minus eta del over del beta Ijm Ei, and then we write the value of this term here. So, you get beta Ijm plus eta delta Ij Xim. So, back propagation update steps are, say, alpha I plus 1 kj equal to alpha I kj plus eta delta Ik Zij. Delta Ik is equal to Eik gk1 Vik is equal to alpha naught k plus Zi transpose alpha k. Then beta I plus 1 Jm is equal to beta Ijm plus eta delta Ij Xim, and delta Ij here is equal to Fj1 Uij plus summation over k delta Ik alpha I kj. Uij is equal to beta Ij naught plus Xi transpose beta Ij, and eta is the learning rate parameter. So, these are the back propagation update steps which we obtain. So, after assigning all the connection weight values in initialization step, the algorithm has the following two steps. First one is the feed forward pass. So, inputs enter the node from the left and emerge from the right of the node. So, we initialize the weights, then we enter the input from the left, and then it emerges from the right node. Output is computed in Vik equal to alpha naught k plus Zi transpose alpha k. Alpha k is this vector and Zi is this vector. Then the results are passed from left to right through the layers of the network. Then we go to back propagation pass. Network is done from right to left. First we have initialized the weights, we move from left to right, we get the output, and then we move from right to left, layer by layer, starting at the output layer. Error is computed at the kth output node and multiplied by the derivative of the activation function to give the sensitivity at the output node. Weights alphas feeding from output node are updated. So, we update the weights alphas. Then sensitivity is computed at the jth hidden node and update weights betas feeding into the hidden nodes. So, we update betas. and then we repeat this process until some suitable stopping time. So, this is how we get the weights using the back propagation of errors algorithm. To summarize, back propagation algorithm involves two main steps. The forward propagation, inputs are passed through the network to generate predictions, and activations are computed sequentially for each layer. So, we pass the input through the network, ultimately we get the predictions, and then we also compute the activations sequentially for each layer. Then we move to the back propagation. Errors are propagated backward to update the weights. So, we use the errors to update the weights, and gradients of the loss function with respect to the weights are computed layer by layer using the chain rule of calculus. So, this is how we have proceeded in the previous case of single hidden layer also, and then these gradients are used to update the weights through optimization techniques such as gradient descent. For the initial values, suppose we start with all the initial weights equal to 0, then it creates problem. It leads to 0 derivatives, and then the algorithm never moves. If we start with large weights, then we obtain poor solutions. So, usually we start with weights near to 0, and if the weights are near to 0, then operative part of the sigmoid is nearly linear. So, basically if you are using small weights, then the model starts out nearly linear, and when we update the weights and the weights are increasing, then the model moves towards non-linearity. So, in fact, starting with the weights near to 0 means we are starting near to linearity, and as we update the weights and weights increase, the model starts out nearly linear, but it becomes non-linear. Usually, initial values for the parameter estimates are chosen using a small random generated, say suppose you take uniform distribution which has very small variance. So, you get small initial values of the parameters. So, we randomly generate the small initial values for the parameter estimates, and then we move further, we update the weights. Now, we consider different learning modes. There are 3 learning modes which are usually used for running the back propagation algorithm: online learning mode, stochastic learning mode, and batch learning mode. In online learning mode, each observation xi, yi for I equal to 1 to n is dropped down the network in sequential fashion. So, we start with I equal to 1, we drop down the observation x1, y1, next we drop down the observation x2, y2, and then we adjust the estimates of the connection weights. Then we drop down x3, y3. Again we update the weights, we adjust the estimates of the connection weights, and so on. So basically what we are doing, we are dropping down the observations one by one in sequential fashion, and then we adjust the estimates of the connection weights each time. So this is how we work. Drop down x1, y1, carry out feed forward and back propagation algorithm yielding updated connection weights. Then we drop down x2, y2 and further update weights, and so on. Then we stop the process after the last observation xn, yn. So we update the weights as the observations come. Then we consider stochastic learning mode. In stochastic learning mode, we consider all the observations and then we choose an observation randomly. So from the n observations, we choose an observation randomly from the learning set, drop down the network and weights are updated. Each observation is dropped down once and only once, but in random order. So the only difference between these two learning modes is that in online learning mode, we have a fixed order of dropping down the observations. First we drop down the first observation x1, y1, then x2, y2 and so on. Whereas in stochastic learning mode, the observations are chosen randomly from the learning set. Then in batch learning mode, n observations in the learning set, which is also called an epoch, are dropped down the network, and weights are updated by summing the derivatives over the entire learning set. So in this case, we are using all the observations available in the learning set at a time, and the weights are updated as say alpha I plus 1 jk is equal to alpha I jk plus eta summation over h equal to 1 to n delta hk z hj. So we take summation of derivatives over all the observations, and then beta I plus 1 jm is equal to beta I jm plus eta summation over h delta hj x hm for all h equal to 1 to n. And this process is repeated epoch by epoch until ESS becomes smaller than some present value. So we iterate this process epoch by epoch. Now when all training samples are used to create one batch, so in a particular batch we are using all the training samples, then the learning algorithm is batch gradient descent. And when batch is the size of one sample, so we form a batch of size 1, then the learning algorithm is stochastic gradient descent. And when the batch size is more than 1 but less than the training data set size, the learning algorithm is called the mini batch gradient descent. So these are the three possibilities. So you can use all the training samples to create one batch, and in that case the algorithm is batch gradient descent. If the batch is of size 1 and then you are randomly selecting the batch, that is, you are randomly selecting the sample, then the learning algorithm is stochastic gradient descent. And suppose the batch size is somewhere between 1 and all the training samples. It is more than 1, but less than the training data set size. Then it is called mini batch gradient descent. Now we consider input scaling. Say you have input data, and then we use this input data for fitting the network. But before using this input data for fitting the network, we usually scale the inputs. We usually scale the inputs so that it lies in interval 0 to 1 or -1 to 1, or sometimes we standardize the input so that it has mean 0 and unit variance. And for standardization purpose, what we do, from each input observation we subtract the mean and we divide it by the standard deviation. There is one more problem. One has to decide the number of hidden nodes and number of hidden layers for fitting a network. Then Occam's razor principle is that keep the model as simple as possible while maintaining its ability to generalize well. Means it should be as simple as possible, and the predictions should be accurate, or it should maintain the ability to generalize as well. Now, when we employ cross validation for selecting the number of hidden layers and the number of nodes in each hidden layer, then the presence of multiple local minima at each iteration may create problem. The problem is which solution should be used for each round of cross validation. Then one can use the trial and error. Say you can decide on the basis of the context of the problem or trial and error. Then what is the role of each layer? A network has many hidden layers, and then what is the role of each hidden layer? Actually, each layer extracts features of the input for regression or classification purpose. So, the role of each hidden layer is to extract different features of the inputs, and then ultimately combining all these features, we get the output at the output node. Then use of multiple hidden layers allows construction of hierarchical features at different levels. You have multiple hidden layers in your network. Each hidden layer is extracting some feature of the input data, and then we combine all these multiple hidden layers for getting the output. So, use of all these multiple hidden layers allows construction of hierarchical features at different levels, and then ultimately you get better outputs or better predictions. Overfitting and network pruning. Basically, you want to reduce the number of parameters and also keep performance characteristics. So, if you are overfitting the model, means your model is too complicated, it has a large number of parameters. So, you may like to prune the network. you may like to set those parameters equal to 0 which are very small or negligible, or which are not playing any important role in the prediction of output. Further, you also want to keep the performance characteristics of your model. So, you may set insignificant parameters equal to 0, which is the optimal brain tuning. Means the parameters or nodes which are not playing any crucial role in the output should have the weight 0. Now, one of the option is shrinking parameters towards 0, and then we minimize ESS lambda omega, where ESS lambda omega is defined as ESS omega plus lambda p omega. Here lambda, which is greater than or equal to 0, is the regularization parameter. Obviously, for lambda equal to 0, this part vanishes. So, the problem is simply to minimize ESS omega. But when we add this part, so this part considers the error sum of square, and then this is the penalty part. You are penalizing or you are regularizing the number of parameters. So, P is the penalty function or complexity term. So, through this part you are controlling the complexity of the model, and through this part you are optimizing the model. Lambda usually estimated by cross validation. So, for estimating lambda we use cross validation. Just remember that what we do in Lasso. In Lasso also, while fitting a multiple linear regression model, we have a penalty term also along with the error sum of squares. So, in the method of least squares, we minimize the error sum of square, then we add penalty term in Lasso. So, we are basically penalizing the complexity of the model. Similarly, here also we have added this term which controls the complexity of the model, and just like in Lasso, we can use cross validation for estimating lambda. P omega is equal to summation over L omega L square. So, this is actually weight decay penalty. These omega L include both alpha j m and beta k j. All the parameters are included in omega L. Or one may take P omega equal to summation over L omega L upon W whole square divided by 1 plus omega L upon W square. This is called the weight elimination penalty. Here W is a pre-assigned free parameters such as say norm of omega square. So, you may take W equal to norm of omega square. Now, if norm of omega L is much smaller than W, then the connection weight has insignificant contribution and it may be dropped from the network. And if norm of omega L is much larger in comparison to W, the connection weight contributes significantly and it should be retained in the network. So, this is the advantage of using the penalty term. It may drop down some of the connection weights which have insignificant contribution, and it retains the connection weights which have significant contribution. So, initially what we do, we start with lambda equal to 0, means there is no penalty term, and then we fit the network. So, we have unconstrained network weights, there is no penalty, there is no constraint. Then we adjust the solution by increasing the value of lambda. We keep on increasing the value of lambda. Say we take small increments in the value of lambda and we adjust the solution. So, each time we increase the value of lambda, some of the weights may drop down. The weights which are not contributing significantly. Now, if input data is high dimensional, then one of the possibility is that you use principal component analysis. You have very high dimensional input data. Then to reduce the dimension, you can proceed like this. You use the principal component analysis, reduce the dimension of the data, and then we estimate the parameters of the reduced size artificial neural network. Now, this is a good option when you have to fit artificial neural network for high dimensional data. Use principal component analysis for reducing the dimension of the data, and then we fit ANN for this reduced size data and estimate the parameters of reduced size ANN. Now, there is a problem with multi-layer perceptron. It is not invariant for many transformations, say such as translation, rotation, mirroring or scaling. Say this is your original picture and this is the translation. You have used the transformation translation. This is the rotation, then mirroring, or you have rescaled the image. Similarly, for data also, you can use different sort of transformations like mirroring or scaling or translation. You may change the origin or scale. Now, multi-layer perceptron is trained for learning a map from input to output, where input is from a fixed location. So, once at the input layer, whatever transformation you have done, say whether you have rescaled the data or whatever transformation you have done, ultimately you are fitting or you are training the multi-layer perceptron for that particular input data. Now, it is not feasible to train the multi-layer perceptron for all possible transformations and combinations, and then multi-layer perceptron is not invariant to such kind of transformations. So, multi-layer perceptron may not be able to identify the digits or images in the presence of these transformations. So, suppose you have to identify such kind of images using the multi-layer perceptron. Then since multi-layer perceptron is not invariant to such kind of transformations, you cannot use multi-layer perceptron to identify such kind of images. Or similarly for digits also, say suppose you are using multi-layer perceptron to identify the digits. Say you have to identify A, or somebody has written A like this. So, he has rescaled A, or there is some other kind of transformation. A is written like this. Now, MLP is not invariant to all such kind of transformations, and you cannot use MLP to identify these digits. So, you require some alternative network or at least some alternative layers for such kind of problems. In your network, you require some alternative layers, and one of the option which we will discuss in the next lecture is convolution network. So, backpropagation algorithm is an important algorithm for training a neural network. In this lecture, we have discussed the backpropagation algorithm. In particular, we have discussed the backpropagation algorithm in detail and its different steps for the network involving single hidden layer. In fact, backpropagation algorithm has two steps or two propagations. Forward propagation, where we enter the input and we pass it through the network, and ultimately it yields predictions. And then backward propagation, where these predictions are used for the obtaining the errors, and these errors are passed backward to update the weights. We have also discussed the three learning modes for backpropagation algorithm. Online learning mode. In online learning mode, we enter the data one by one, means first we enter the first observation, then we enter the second observation, and so on, and each time we update the weights. In stochastic learning mode, we enter the data one by one, but each time we select the observation randomly from the learning set. So, the only difference between online learning mode and stochastic learning mode is that in online learning mode, we select the observations in a sequential manner, whereas in stochastic learning mode, the observations are selected randomly. And then we have also discussed the batch learning mode. In batch learning mode, we enter all the observations in the learning set at a time, or we may select a set of observations from the learning set to form an epoch, and then we enter the epochs for updating the weights. So, I am going to stop here. Thank you.
I am A.K. Sharma, and I am professor of sociology at IIT Kanpur. The question I am going to address is what is urbanization? Urbanization is essentially the process of population concentration, which means that if more people start living in a smaller number of places, or if the distribution of population becomes more unequal, like more people living in places like Bombay, Calcutta, Mexico, then we say that the urbanization is taking place. Essentially, it means increase in percentage of population living in areas or localities which are defined as urban. Urbanization is a new phenomenon, of course, a post-industrial phenomenon. About 200 years ago, hardly 5% population of the world lived in urban areas, and today more than 50% population of the world is living in urban areas or localities which are classified as urban. You will be happy to know that according to 2011 census of India, in our own country for the first time, increase in the urban population has been greater than the increase in the rural population, though India is not so urban as the developed countries, and about 31% population of India only is living in urban areas. We can believe that in 10 years, 20 years, 30 years time, India will also be more urban, at least more urban than what it is. It may not be 80%, but certainly it will be 35% or 40%. Now, how is this urban locality defined? Because this definition of locality as urban or rural is crucial to measure level of urbanization. I will give you definition of our own country. In Indian census, an urban locality is defined in two ways. There are statutory towns and there are census towns. All places with municipality, municipal corporation, cantonment or notified town area committees are called urban. This is statutory definition. According to demographic definition, there are three main criteria. If a locality has more than 5,000 people, or 75% of male labor force is engaged in non-agricultural activities, or the density of population is 400 per square kilometer or 1000 per square mile, then we say that the locality may be classified as urban. There are many other additions to this definition. Now, we have the concept of urban agglomeration and many other things, but essentially this is how urban population is defined in India. And as I said that urbanization is associated with economic development and industrialization, same is the case with India. About 100 years ago in India, only 11% people were living in urban areas. Today 31% are living in urban areas, and this is obviously linked with economic development of the country, growth of per capita income and industrialization. I remember that in one 5-year plan it was mentioned that today this urban population can grow by way of natural increase of births minus deaths in the urban areas itself, or through rural to urban migration. Today nearly 60% contribution to growth of urban population is due to rural to urban migration, and this is going to increase. This is essentially what urbanization means. Urbanization means growth of population in localities defined as urban in relation to population of localities defined as rural, and I have given you Indian definition. Thank you very much.